Okay, guys, sorry about the delay. I was caught up in other things. Turns out there's a weird air pollution in my lab, and then it's kind of emergency. I have to fix that. Okay, so are most of you now in Charlottesville? Okay. Yeah. Okay, so that's nice. Okay, so let's get started. Okay, so today we're going to talk about probably one of the most important thing in quantum mechanics. That's the Schrödinger equation. Okay, and if you guys have read the quantum mechanics textbook, you notice that in most textbooks it's just one line, right? This is Schrödinger equation. But today, let's hope that we can get you guys convinced that Schrödinger equation is actually very natural. Okay, it's a natural result coming from saying that electron is a wave. Okay, so a little bit history behind the Schrödinger's equation. So last time we already talked about the Schrödinger's equation actually was inspired by the Breuil's thesis, where he said the electron is a wave. Okay, and then his advisor at the time, Schrödinger at the time is a research scientist, I think in his mid-30s, and then his advisor, the boy, is a well-known professor at the time, suggests that if this is a wave, then you need to have a wave equation, to describe the wave, right? Because we know that previously we learned that for particle, you describe the particle motion by using F equals ma, right? It's a force. And then for the wave, it's a differential equation. Okay, it's a differential equation. So despite the fact that we don't know what the Breuil means, electron is a wave, right? Like he didn't really say what type of wave, what exactly that is. But then at least you need to look for a differential equation that captures the motion of this wave. Okay, so now if we think about this, and it seems that this is a very difficult task, because how do we derive mechanical wave equations? For mechanical wave, we kind of say, there's a chain of molecules, and then they are interacting with each other, right? We say there's a spring in between them, and then there's a force, and then you can calculate this force by using F equals ma, and then you can say this is psi ui, ui plus 1, ui plus 2, ui minus 1, and then you get this differential equation of ui on x. So fundamentally, although the mechanical wave is described by a differential equation, but that differential equation comes from F equals ma, right? And that differential equation comes from the fact that you have individual molecules in your mechanical wave, and then they can interact with their neighbors. Okay, that's a source of differential equation from classical wave or mechanical wave. Now, let's think about the wave in the hydrogen atom, right? So the Breuil says that the electron in a hydrogen atom is a wave. Okay, so there's only one electron. It's impossible to come up with the equation like mechanical wave, right? Because mechanical wave, you have to have many molecules and they interact with each other. Here you only have one electron. So unless you assume electron can interact with itself, which is actually a very interesting topic, how electron interact with its own field. Okay, but that's not the solution here. Okay, so electron, we're assuming it cannot interact with itself at this point, then how is there a wave equation? Right? There's a simple point here. Okay, so this is kind of difficult if you try to go with F equals ma. Okay, and then so this comes with the second thing is that at the time when we introduce the comparison between particle and then wave, okay, did you guys remember that there's actually a second way to derive F equals ma for the particle? Okay, it's not using F equals ma, but using the energy of the system. Right, we call that analytical mechanics. We can go over this very quickly. Suppose you have a box attached to a string, and then you can go this back and forth. So this is typically a harmonic oscillator. Right? If you write down its energy, let's say the energy is expressed by h, the energy, you say, okay, it has kinetic energy, right? And then it has potential energy. And then for the kinetic energy, okay, you see that there's a velocity, and then it's possible to make it to a, right? A is the acceleration, it's the rate of change of your velocity. So what you can do is that you can do partial h, partial v, okay? Partial h, partial v give you mv, right? This gives you mv, and then you do a partial t here. Okay, so this gives you ma. And then for the harmonic oscillator, the force here is minus kx, right? If you go that way, go towards x direction, then the forces pull you back. That's why there's a minus sign here. So the force, we can see, okay, it must come from the potential energy. So here you will see, okay, partial h, partial x will give a minus sign here, will give you minus kx, and this is your force. Right, this is your force. So in total, what this harmonic oscillator is telling you is that instead of writing down F equals ma, you can also write down the energy of the system, and then use this differential equation, which is, let's write it down here. Let's see, probably write down here partial t, partial energy, partial velocity, and then this is ma equals F, right? F is, okay. So what it tells you is that here is that you don't have to know the force of the system, of the particle. You can write down the energy, and there's a way to use this energy to connect to the force and give you exactly the same dynamics for the system, at least in the classical mechanics case. Okay, so this is what Schrodinger did here. Okay, this is what Schrodinger did here, and it kind of makes sense. Is that why not write down the energy of the electron first, right? Because that's what you need to do eventually, right? So when you write that down, the energy, it's fairly simple. Kinetic energy minus this is a potential energy, right? Nothing quantum here, just a classical energy expression of an electron circulating around the nucleus. Okay, and then you can also say, okay, I don't like mv. I like to write it down as momentum. That's also fine. Then you can write it down as momentum. Okay, now this is a time that we have to apply some assumptions than made by de Broglie. So we say that, okay, this is the energy of the electron. According to Albert Einstein and according to Max Planck, how do they write down the energy of each individual energy pack? They write down as there's an energy, and it's h times the frequency, or h bar times the angular frequency. Right, so this is how they write down the energy. Okay, maybe if you say maybe if this is, you want to apply this to a quantum mechanical case, maybe this is a connection here. And then the second thing is that the momentum, we learned from the photoelectric effect that if you have this as your energy of a photon, then by using Maxwell equation, you can show that the momentum of the photon, okay, is h divided by lambda. Or you can also write it down as h bar k, where k is a wave vector. And in de Broglie's thesis, he assumed that this is also true for the electron, okay, without proving anything. Okay, so if you look at this, okay, this looks like a connection, looked like a possible connection between classical and then some quantum assumption people made to make their theory agree with the experiment. Okay, so let's see how this can work on a wave. And just to make things extremely simple, let's assume that we're going to use the simplest wave, that's the plane wave. Okay, plane wave. And is everyone familiar with complex number? If someone is not familiar, raise your hand. Okay, so the plane wave, I think in real number, right, people usually write it down as the plane wave is a wave amplitude, cosine, and then omega t minus kx, or another amplitude, sine omega t minus kx. Right, this is usually how people write a plane wave. It's just a sine wave. And then the reason we call it plane wave is that it propagates along x direction, and then the wave amplitude has no relationship to y and z coordinate. Right, so if you look at it, you cut a slide, it looks like the face of the wave, entire wave, is a plane. Right, it's a plane that's perpendicular to the x direction, which is your propagation direction. Okay, so that's why it's called plane wave. And the reason that, well, we don't like to use cosine and sine is that if you take derivative of cosine, it becomes minus sine. If you take derivative of sine, it becomes cosine. Right, so you kind of need to keep track of this. So a different way to write a plane wave is to write it down as, right, is to write it down as a complex number, right, exponential of this, and then you guys can look for the definition, but this is okay. There's a minus sign here, so that's why there's a minus sign here. And then the reason we choose minus sign is just out of courtesy. You can always use plus sign as well. There's no difference here. Okay, so let's say this is a wave for the electron. Okay, this is a wave, very simple, a plane wave. Now, how can we get the energy of this wave if we assume the energy is this? One way is that you look into it, okay, there's omega, right? That's one way, but is there another way that, let's say, if you have a wave here, is there other way that you can do something to this wave so that the energy show up in the front? Any guess?
Take the derivative?
Yes, take the derivative, right? Take the derivative. So if you take the derivative of t of this plane wave, okay, we are only doing this on plane wave. If this is not plane wave, things will be much more complicated. Then what you will get is you will get minus I omega and then partial, and then your wave, right? And then if you want to make it into h bar omega, you can always add h bar here. Okay, then you add a h bar here. And then you can get rid of the minus I sign by applying an I here, right? Then I plus I times I is minus 1, and this goes away. And this is not, this become equal. Okay, so this is interesting. It looks like if you do a time derivative on your plane wave, it gives you the energy of that wave in quantum mechanics assumption, right? If we assume that the energy is like this. Okay, and the derivative in quantum mechanics in general we call it operator. Okay, operator. We can call this operator, let's say it's the operator gives you energy, so you say OE, right? Okay, so this is the operator. Now, how about momentum? How can we do the same thing to get momentum? So the momentum is that you do something to a wave and then you want to end up with h bar k, right? H bar k is the momentum. So you want to get h bar k of your wave. And then you can see, okay, here is k. So you should take derivative of x. Okay, this gives you ik. And then you don't want I here, so you can put I here. Okay, so get rid of the I. And then you want h bar. You want h bar here. Okay, so by doing a derivative on position, it gives you momentum. And then, well, you might be wondering, okay, it looks a little bit weird because previously in classical mechanics, we say that if you do a derivative of position over time, it gives you velocity, it gives you momentum. But right now you're doing a derivative on position, and that gives you momentum. Okay, it's a little bit tricky here, but then the way to understand this is that if you think about this as a function, okay, doing this is really moving the function. Okay, and we can talk about this later when we introduce after introducing the Schrodinger equation. But right now, let's call this operator, okay, P. It's an operator where if you act on this operator, if you act on a plane wave, it gives you momentum. Now, can anyone guess how to get Schrodinger equation from here?
But isn't the operator giving the momentum multiplied by the original?
Yes, by the momentum and multiply the wave itself.
So would you just divide it by the wave itself to just get the momentum, or?
That's a good thinking, yeah. Yeah, but yeah, let's say, how can we go from here to Schrodinger equation if you know the energy of the system is like this? If you can do this, your name will be on textbook.
Substitute?
Good guess, but not really. So this is actually something kind of interesting, like this is actually why we often suggest students to try to do some research in undergrad or even try to go to grad school, is because there's a difference between learning a material and then creating something new. Because no matter how simple it looks like, when you make that logical jump, when you make that intelligent jump, it's always hard. Okay? And here I can tell you guys the answer, and you'll be shocked how easy it is. So from this equation, we know that the energy, if you want to write it down as energy, multiply the wave equation, right? The wave equation, you can write it down as this. Right? This is what we have here. And we write down this way, okay, it's a differential equation, which is great because for wave equation, we want differential, right? And the second way to write down the energy is here, right? You have your energy from classical mechanics. Energy is also momentum squared divided by 2m plus, this is a potential energy, right? Okay, this is a potential energy. You can use for the electron in hydrogen atom, or you can use a different potential energy, for example, for harmonic oscillator, right? It would be kx squared. Okay, so this is also the energy of the system. So I multiply this also with the wave function. And this equation must match, right, if energy is really h bar omega. Right? We're just simply writing energy in two different ways. One is in a classical way, the other is in a quantum way that is assumed by Planck and Einstein. Right? H bar omega is the energy. This is also the energy. Now the next step is that for wave equation, you always want it to be a differential equation, right? It has to have differential on time and also differential on space. And how can we do that? You look at this momentum term here, and you realize that momentum is also this. Right? Momentum is also this. Momentum times h is equal to h bar I partial x, your wave function. So momentum square equals to minus h bar square partial x. Right? So you substitute this in, and then this becomes minus h bar divided by 2m partial x square plus vx, your wave function. And this is the Schrodinger equation in one-dimensional space. And we derived this within half of the whiteboard, but then in reality it took scientists 25 years to figure this out. Because, well, yeah, it's just that hard, right? So when you look at it, okay, when you know, oh, okay, that's the Schrodinger equation, energy equals energy, makes sense. But then when you're working on it for the first time, it's very easy to miss that, okay? Any questions here? For example, like, there's any notation. Does everyone understand the notation for this Schrodinger equation?
So what makes it one-dimensional again?
So one-dimensional here is the fact that we're only is this two, one-dimensional. So you see here our wave is only propagating along x direction, right? And then we say the momentum is h bar k, k is along the x direction. So this momentum is actually a momentum on the x direction, right? So the y and z, we are assuming that it doesn't move. Does that make sense? Yeah, and then also the same for the potential energy, right? The potential energy, we're writing it down as a function of x, right? So when you're a function of x, that means when you can move freely on y and z position, right? Because there's no potential energy, right? So that's why it's actually called a one-dimensional Schrodinger equation. And then it's actually quite straightforward to make it into three-dimensional, okay? Because if you want to know momentum of y, right? Operator of momentum on y, then it's the same thing, but then you change the derivative of x to derivative of y, right? So a three-dimensional case would be right. So the wave function become a function of x, y, z, and t, right? 3 dimension of space and then 1 dimension of time. And then you have momentum on x direction, momentum on y direction, and momentum on z direction. And then your potential energy become a function of x, y, z. So three-dimensional three-dimensional potential energy. So this is a three-dimensional Schrodinger equation. Okay. Any other things you guys want to know about this equation? Any other questions?
What did you get from p times phi equal to h bar over I partial of x phi to p squared equal to?
Oh, okay. Yeah. Yeah. So okay. So let's write it down here. So I think you're asking how we simplify this term, right? P squared per psi.
Well, no, how'd you get, because you have p times phi, and then you get to p squared.
Yeah, so let's do it this way, okay? So P squared per psi equals to P times P per psi, right? P times P per psi. And then we already know P per psi. We already know P per psi is this. Right, this makes sense? We're just copying this here. And then the next step, okay, this is actually a very good question. So naively you can think, okay, now let's switch them. You can put this in the front and then P per psi, right? So you have P per psi again. And then we know P per psi is this, right? So become HI, also HI, and then per psi, right? And then you have if you look at this, then you have h bar square, I times I is minus 1, and then you have derivative of x, derivative of x, so that you have second derivative of x. Does that make sense?
Yeah, it makes sense. I don't see how that moves legal, moving the p next to the phi, but
Oh, you mean, wait, do you mean here?
because you said because you moved the p right next to the phi.
Yeah. So yeah, this is a very very good question. So in reality, what happened is that when people see this, in quantum mechanics, then people make the assumption that this is the operator of momentum. And then the assumption is that, okay, then if you want to change something from classical mechanics to quantum mechanics, what you do is that you simply change P into OP, which is h bar I partial x. Okay, so this is actually a postulate. This is assumption. And the assumption, well, you can say, okay, we derive it, but then when we derive this, we're assuming the momentum is h bar k, right? So we're always making assumption. So when you track back, you can say, we can make assumption that for plane wave, this is the momentum, or you can make the assumption that the momentum is represented by an operator, which is h bar divided by I partial x. Okay, so these two are equivalent in terms of if you look at the framework of quantum mechanics. Okay, you can derive one to the other. Okay, does that answer your question?
Yeah, thank you.
Okay. Yeah, so please ask questions, because like the entire class will depend on this, and then if somehow you don't understand this equation, then you have troubles. Okay.
So are you basically assuming also that the wave of the electron is a plane wave?
Oh, that's a great question. Okay, that's a great question. No. Okay, the answer is, this is a very critical point. So although we say we derive Schrodinger equation, but no, we didn't derive it, we guess it. Right? We start from a plane wave, we write down some relation between energy and momentum, and then we say, okay, the energy must equal to energy. Right? So, and this works to, in our derivation, this works for plane wave. Right? Plane wave, it works for plane wave. But then Schrodinger took next step, right? If it worked for plane wave, it should work for all waves. Because all waves should obey the same wave equation. Right? Let's say if you have a string on a guitar, it doesn't matter what waveform you currently have on your guitar, they're always the same wave equation. Right? So this is again the assumption that, okay, if it worked for plane wave, it must work for all the waves. So to answer your question, okay, is that when writing down this equation, it's not automatically correct, right? Because we made quite a few assumptions here, right? So there has to be a way to compare this with the experiment, and then show that, okay, whatever result coming out from this Schrodinger equation actually match with your experimental observation, and that's the way to prove quantum mechanics. That's a way to prove Schrodinger equation, and that's a physics, chemistry, and biology way. It's different from mathematics. Mathematics is that you make a few assumptions, like 1 + 1 = 2, and then like two parallel lines never cross each other, and then you prove the entire system. That's mathematics. Physics is that you come up with equation with reasonable argument, and then prove that equation by doing experiment. Okay, so there's a very subtle difference here that separate, well, we have to call math also science, experimental science and then pure math. Okay. Other questions?
I guess from purpose of things
Mm-hmm.
is like when you say wave equation,
Mm-hmm.
I kind of think the definition might be something along the lines of like an equation that describes both the amplitude of like the individual things in the wave and also like the position of the wave itself. Would
Yeah.
that be like the definition?
Yeah. Well, you're asking great questions. I mean, if you're 100 years older, you could win the Nobel Prize. So this is actually so you asked two great questions, because the first great question, okay, of whether this apply to plane wave, that would lead to how we verify Schrodinger equation is correct. That's actually the second half of Schrodinger's paper, how he compared this to experiment. And then the second, well, your second question is, what is this wave, right? What exactly is this wave? And the answer at this point is we don't know. So to this point of this class is that we don't know. Of course I know, but I'm not telling you right now. And to answer this question, actually there's a long debate, okay, between like there's a debate between Schrodinger and then Heisenberg and then Schrodinger, Bohr, and then also Bohr and Albert Einstein, and then eventually I think it's Max Born came up with the probability explanation that actually won the Nobel Prize, I think in 1957 or somewhere. Okay, so yeah, the question is great. It's like, what exactly is this wave? Right? We write down a wave equation, but we actually don't know what this wave is at this point. Okay. Other questions? Okay. So one thing that's, I know that the UVA encourage everyone to become a leader, right? But how to become a leader? A leader is really, at least in terms of science, it's actually to ask the right question. And then your team will work on the details. Okay, so the leader is the one to point the direction. And then, so that's actually asking great questions in this class is very important. Like, I'm pretty sure that most of you will forget how to solve Schrodinger equation a year after this class. But then, at least if you think about this, and then, there will be something left in your brain. Okay. Now, where's my note? Okay. Now let's move this Schrodinger equation to a more obvious place. Okay. And then we write it down as three-dimensional equation. And this is actually a real story that in many qualifying exam, one of the questions is to ask you to write down Schrodinger equation. And then I know this, like when I was in Caltech, there was one of my friends that failed to write down Schrodinger equation because she hasn't used it for like many years. And then the committee immediately stopped the exam and then actually failed her, on the site. And the reason for this is actually I think it kind of makes sense. It's because Schrodinger equation is just energy equals energy, right? So if you really understand Schrodinger equation, then you should be able to write it down without, memorizing it. Okay, and then here where we get it is that the assumption is from h bar omega is your energy, and then your momentum is h divided by lambda, or h bar k, Okay. And then this is the operator that gives you the energy, h bar omega, and this is the operator that gives you the momentum. Okay, give you the momentum. And then although we derive it from plane wave, but then the assumption is that, okay, it should apply to all wave because in a system, for example, in a guitar, all different waveforms actually obey the same wave equation. Okay. So now when you have this equation, we finally caught up with the textbook. Now it's page 1 in the textbook. Okay. So two obvious questions. One is that what is psi? Okay, what is psi? And unfortunately, we need to we can only talk about this on Thursday and then possibly next Tuesday because it will actually take 1 or 2 hours to explain, okay, in a reasonable way what psi is. Okay, and the second question. Let's ask the second question. And when Schrödinger published his paper, actually, when he won the Nobel Prize, he didn't explain what this wave is. Okay. And the second question is, how do we know this equation is right? How do we know it's correct? And from the history point of view, this Schrödinger equation is actually not the first equation Schrödinger wrote down. Okay, Schrödinger wrote down the equation Schrödinger first wrote down is in the form of special relativity, because when you have special relativity, the energy is not just kinetic energy plus potential energy, right? Because when things travel extremely fast, their mass change, and then there's additional energy. So when Schrödinger first wrote down this equation, it's in the special relativity form. And then he actually ditched that. And later people rediscovered that equation, and that equation is now called the Klein-Golden equation. And Schrödinger ditched that equation for a reason. Later people pick it up for a reason, and then it's very interesting that actually Schrödinger's, the Klein-Golden equation, which was the equation Schrödinger first discovered, was actually right in certain situation. Okay, so how do we know this equation is correct? Which experiment should we compare this equation to? We introduced 3 different experiments in the previous class. We have the black body radiation, which was solved at the time by assuming that light could be particle. And then we have the photoelectric effect, which was also solved by assuming light could be particle, could be photon. And then the third is the hydrogen spectrum, hydrogen atom emission spectrum that has discrete discrete emission wavelength. And then that was solved at the time by de Broglie, assuming that electron is wave. So which experiment should we pick to verify the Schrödinger equation? Any guess?
Hydrogen spectrum one?
Yeah, because that one used the assumption that electron is a wave, right? And then we just wrote down a wave equation, so that if you really want to verify this, you have to compare it with the hydrogen atom emission, right? So let's just briefly review what that is, right? You have charged tank with a lot of hydrogen atom, and then they emit light. And then when you look at the spectrum, instead of seeing a continuous spectrum, you see, individual lines, and then you have the frequency of the light is proportional to a constant, and then there's 1/1 integer number, and then another integer number. Right? That's the hydrogen atom spectrum, and then there's integer number here. So you can almost be sure that by using, when solving this equation, if you apply boundary condition, right? That's how we get integer number for solving a string. Okay, you fix a boundary, you get a period, you get n equals 1, 2, 3, 4, right? So here again, maybe by applying boundary condition, you can get integer here, and then that might lead to a solution looks like this form. Okay. So the question here is that it's kind of obvious. If we don't know what wave function means, how can we solve this equation? Right? Like, what are we really solving if you don't know what it means? Right? And you know, Schrodinger did something that probably all grad student or all researcher would do, is that he looked at this equation, he thought, okay, I can solve this. Right? It doesn't matter what this wave function means, but then this is a differential equation. This is a differential equation, and then it describes an electron that's circulating of a positive charge, and then there's a spherical symmetry of the system, right? The potential energy is only related to the distance. So this equation, he knows how to solve it, so he just solved it. That's what he did in his research paper. Okay, he didn't ask what this means. Well, he asked himself what this means, but then in reality, he just solved this equation, and then from the mathematical result, and we look back and see, okay, what could possibly mean for this wave function? Does everyone follow this logic? It's like when you see an equation, just solve it. Okay, so we have about 15 minutes, so we have 25 minutes, so I will quickly solve this equation here. Okay, this is a standard hydrogen atom Schrodinger equation that was, the solution was in, I think it's in all the textbooks. And then this is usually required for physics department, but then since none of you, I think, would be working with hydrogen atom in the future, so we're not requiring the solution, how to solve this in homework or exams, right? So this is just basically for your knowledge, what the solution will look like. You'll be asked to solve a much easier equation and more practical equation in your homework and exams. Okay. So if you look at this equation, okay, the wave function is a function of x, y, z, and t, so 4 different variables. And I think some of you must have taken differential equations, right? So what should you do? What method should you apply here when you have multiple variables? Does anyone know? So method of solving differential equation is called separation of variables. Okay, separation of variables, and I will show it here, but also later in the homework and also in the exams, you will solve a much easier equation with the same method. Okay, so the first thing that to deal with this equation now is hydrogen atom. Okay, so and we know R is the distance between the nuclear and the electron is x squared plus y squared plus z squared, right? It's just a distance. Okay, so the first thing you to do, okay, if you want to apply separation of variable, yes, one way you can do it directly here. There's x and y and z. And the way people do it, separation of variable, is that you assume that the function can be, the eigenfunction can be expressed as a function of x times a function of y times a function of z, and then times a function of t. Right? This is the assumption for the separation of variables when you solve the differential equations. Okay, but then one difficulty, if you look at this, one difficulty is this term. You have x squared, y squared, z squared. They are all clustered into one term. Okay, and the reason that this term appears is because we're not using symmetry in our system. The hydrogen atom has a spherical symmetry, right? Because no matter where it is, it can stay on the sphere, and as long as the distance here, r, is fixed, then they always have the same potential energy, right? So this is a spherical symmetry. It's like when you rotate your coordinate, and then as long as the distance is the same, you see the system as the same. Okay, so usually when you solve differential equation, you first observe the symmetry, and then you choose the coordinate that match with this symmetry. Okay, so here the symmetry, of course, we choose would be the coordinate would be a spherical coordinate, right? So one is, it's described by r, and then there's an angle here. Let's see, angle here, theta, and then another angle here, phi. Right? If you want to describe a point in x, y, z components with this spherical coordinate, and you can write it down as yz equals to r sine theta. Okay, r sine theta will give you this line. Okay, and then cosine phi, right? Yes, will give you this side. Okay, this is x, and then you can do the same thing for y, and then do the same thing for z. Okay, so this is how you convert between xyz coordinate and spherical coordinate. And it turns out that, okay, this spherical coordinate is actually widely used, so you can transfer partial x, partial y, partial z into r, theta, and phi. Okay, this one you can just look up in the Wikipedia. You can just type in, let's say, differential equation in spherical coordinate, and then it will give you this. Okay, so if we transfer everything in spherical coordinate, then you will get equation look like this. Okay, I h bar partial t per psi equals to okay, so this is the term that contains r, and then there's a second term that contains theta and also r. Okay, so this is when you convert the Schrodinger equation into from xyz components coordinate into spherical coordinate. Okay. Now I'm not going to go over the details. It's in the notes, and also it's in the textbook, and also it's not required in this class. So if you're getting scared about this equation, making sure that, well, I'm assuring you that you will not ask to solve this in any of your homework or your exam. So the only thing that I'm trying to do here, okay, I'll do it once and then, a few more times later in future lecture, is to show you how the separation of variables work. Okay, so if you look at this equation, the left-hand side, the differential is on t, right? There's an operator on t. So you can call this an operator on t per psi. And what about the right-hand side? The right-hand side has operation on r, theta, and phi, right? So the right-hand side have the operation on position, right? It's actually the same as this. This is x, y, z. This is r, theta, phi. So the right-hand side is operation, let's say, on space, right? We denote it as r. Now let's see how the separation of variable works. Okay. Actually, anytime you can separate the operation of one variable with other variable, you can always apply separation of variables method. So for this form, what we do is that we assume, okay, we can separate per psi t is a function of t times per psi r is a function of r. Okay, this only works for eigenfunctions, not all functions, eigenfunctions. Okay, now we plug this into here. Okay, then what you get is that you get operation on t per psi r equals to operation of r per psi t per psi r. Okay, now let's look at this. Okay, the wave function of t is a function of t, right? It's a function of t. So the operation on position will not affect the wave function of t, right? Because whatever differential you're doing or r you're doing, I'm not taking it, right? I'm a function of t. I don't have r, I don't have theta, I don't have phi in it. So here on this side, you can move the phi t into the front. You can exchange this order. Okay. So operation of r, operation of space act on a function of space. And then you can do the same thing for here. Okay, this is operation of t, act on t. And then this is a function of position. It has no time in it, so that it doesn't matter where this is, right? You can put it in the front, and it's become this. And then some of you might be confused, why are we being so careful here, right? Because in algebra, we learned that a times b equals b times a, right? You can always switch things. But later we'll show that it's actually not the case in operation. Now, everyone follow this step, right? It's just operator here, and then we assume that you can separate these variables, okay? And then we get to here, okay? Then the next step we do is that we divide this equation on both sides. We divide it down by the wave function itself. The wave function itself. So partial r and then this is equal to Okay. Now, it's very clear these two can cancel each other, right? Psi r and psi r, they're doing nothing here. Okay, it's in front of the operation, there's nothing happen here. So you can cancel this term. You can also cancel this term, right? On the right-hand side, psi t and psi t are not doing anything. Okay, so you cancel them. Now my question is, can you also cancel this, psi t and psi t, on the left-hand side?
No.
No, why is that?
Because then you just be left with the partial with respect to, you just be left with the operator, and the operator can't do anything.
Yeah.
Without it.
Yeah. So let me give you guys an example, very simple example. Suppose you have a function that is, let's say, x, right? And then if you do a differential on it, it gives you 1, right? Differential of x give you 1, right? And what we're doing is an operation on a function divided by the function. So if following this and differential on x divided by x, it will be 1 over x, right? If you do this operation first and then divide down this. Now if you cancel this, then it will be, right? These two are not the same. These two are not the same. So you cannot just cancel terms on top and below, right? You have to make sure that it's not being operated. And the other way to think about this is whatever function you have, after the operation, the function will change, right? For example, here, yes, you're a function of x, but then after the differential, you become 1, you become a constant. You're no longer x, right? So there's nothing to be canceled. Okay. So does anyone have questions here? Okay. Then now let's move on here. Is that we write this down OT psi t divided by psi t equals to O operation of r psi r divided by psi r. Okay. Now if you look at this equation, your intuition could be, okay, this equation looks weird because the left-hand side apparently is a function of t, right? You have operator of t, a function of t, and then a function of t. There's no position here. Okay, so on the left-hand side, you can think of it as it's a function of t. Let's call it ft. On the right-hand side, it's very different. You have operator of position, act on wave function. That is a function of position, and then divided by a function of position. There's no time in it. There's only position. So the right-hand side is a function of position. Now, how can a function of time equals to a function of position? Any guess here? How can that ever happen?
When they're equal to constants?
Yes, exactly, right? So if this is a number, right? If this is a constant, that's the only way that a function of position can equals to a function of time, right? Then this actually reduces your this differential equation of 4 variables into 2 separate set of differential equations, right? It will be ft, a function of t, equals a constant. That's one function. That's one equation, and then this function of position also equal to the same function, same constant, then that's your second equation. Okay, and by solving these two separately, then you get the eigenfunction of your Schrodinger equation. So we will solve this left part here, and then I will get, I will skip this part and then give you the final result. Okay, so the left part, if you look at it, the left part is IH bar partial t act on a function of t equals to the function of t times a constant, okay, times a constant. Let's call this constant e. Okay, does anyone know the dimension of this constant, the unit? Is it length, speed, time? Why do I put e here? Okay, if you look at the Schrodinger equation, it is h bar derivative of t, okay, this is our left-hand side, actually equals to, this part is the kinetic energy plus the potential energy and times the wave function, right? So whatever constant you have here, it must have the dimension of energy, right? So if you solve this equation and finally you get this number E, it's very likely to be the energy of your system because it has the dimension of energy, right? Okay, so let's put E here as the constant, and then let's move the IH bar to this side. And the solution of this, a first order derivative equals to a constant and times your function itself, this gives you an exponential solution, right? This gives you, there's a amplitude, an exponential, and then you have e to the IH bar t. Right? So if you do differential of this, then the e divided by IH bar will come out, and then nothing changed. Right? So this is actually the solution for this differential equation. And then if you accept the fact that E equals to h bar omega, okay, you will see that this gives you e to the minus I omega t. Okay, minus I omega t. So this is actually very consistent. What you assume is what you solved. Okay, and you can do the same thing for the position. Okay, position operator here, and then this one you have to apply separation of variable, two more times because there's r, theta, and phi. Let me skip this part and then just give you the final result. The final result would be your equation is, well, your function r theta phi t equals to r. Okay, it's a special function, and then there's two integers here, n and l, r. Okay, and then there's a spherical function, L and M, also are two integers, and then this is a function of theta and phi. And in the notes, actually, it's written there, okay, what are these special functions? It's actually kind of well known in mathematics. And then apparently you have this e to the minus I omega t, or e to the minus, this is n L m, okay, I omega n L m. Okay, so by selecting different integers, you're selecting different eigen wave functions, just like in a string of the guitar, right? By selecting different integers, you're activating different pitch. Okay, so the important thing is that, let's see, here is, let me use E. Okay. The important thing here is what is E, right? E has the dimension of energy, and then by solving all this, Schrodinger equation, then Schrodinger actually get this. He get 1 over integer square. Okay, 1 over integer square is the energy of this state. Okay, so now this actually matched the experiment perfectly now. So if you have electron circulating here, and then it jumped from one energy level, n equals to m, to another energy level, let's say here n equals to m2, then their energy difference would be a constant times m1 square minus m2 square. And then this energy difference, as far as we know, would be the energy of 1 photon, right? The energy of 1 photon. Okay, so to this end, we show that, what is the Schrodinger equation, where it comes from, and then by solving the Schrodinger equation, you see something that matches with the experiment. Okay, but still at this point, we don't know what the wave function in Schrodinger equation is. Okay, we don't know that, but it just happened that the eigen value of your differential equation matches the experiment result. And then before we go, I want to ask a few questions, and then you guys can think about it. Before the next class, is that first is that, okay, what does this wave function mean? Okay, obviously. The second is that, what does the eigenfunction, what does the eigenvalue mean? Right, we solve the eigenvalue here. And then the third is, what do we mean by saying that you can minus one energy and another energy to get your emission spectrum, to say that the photon energy is one energy minus another energy? Why can we do that? Okay. And the third is that the final thing is that when we're measuring the spectrum of the hydrogen atom, what are we really measuring? Okay, can we measure all this, or what are we really measuring? Okay, so please think about those, and then this is that's it for this class, and I will stay here for 5 more minutes. Okay.
When you do the operator T multiplied by psi equaling operator R multiplied by psi, how can you just have that like by itself without introducing like, because in the original equation, like right above it, you have the operator R times psi, but then you also have minus and then some operator theta, I guess, times psi, and then how can you like leave those out?
Yeah, so in the notation, I should explain this. In the notation I wrote down is that the operator of, one second. I actually wrote down operator of R, and then there's a vector sign here. So that means 3-dimensional R. Include R and theta and phi. So include everything in space.
Okay, so just like factoring.
Yeah. So you can write down as this is actually, you can use a different notation. This is R, theta, and phi. Okay. Yeah.
Thank you. Thank you.